So let's return to the Fibonacci counting problem or computation problem one last time in the context of linear algebra, because it's very often the case that things can be sped up by using linear algebra. So linear algebra, of course, you know mainly as a tool for solving equations and so on, but in fact it's also a very useful tool for making efficient computations. And I'll show you a simple example from the Fibonacci setting, but in fact I think this is a general thing that you should keep in mind when you think about how you design your programs. If there's some way that you can recast your computations in terms of matrices or things that can be put into standard tools from linear algebra, you should do so. For two reasons. One is that there's a theoretical understanding of how you make computations with matrices that is probably better than most situations of mathematical concepts. So you can sort of buy into that by using linear algebra, but perhaps more importantly, these problems in linear algebra, they come up in all kinds of situations. So also in what you might call applied math. And consequently, people have thought a whole lot about how to do these things efficiently. So there are very efficient algorithms for making computations related to operations on matrices, like computing determinants and so on. So, and this is all built into Maple. Right? This is something that I think actually it's very likely that many of these things come from military applications. Unfortunately, this is one of the main sort of driving forces in in the 20th century, that you somehow needed to be ahead of your enemy in terms of making good military decisions, and so you needed to deal with data coming from these kinds of situations like navigation or putting a bomb in people's heads. And so this is something that has been developed in the 20th century to a very high level. And these days, it's actually driven by something a little bit more peaceful, namely computer games. If you want to do things that are sort of 3D and you want to do it fast and want to make it look realistic, that's what you need to do. And so this is something that is very well understood, and you can buy into that by using linear algebra in your computation. So if you somehow, for instance, if you're solving a set of equations and it happens to be linear, if you're not in a hurry, you can just give the equations to Maple and it will solve them for you. But if you are in a hurry, you should reinterpret the linear set of equations into a matrix, given the coefficients from the linear system, as you know from linear algebra, and ask Maple to work on that because it will be much faster. So the example I want to show you is related to the Fibonacci numbers, and this is a good example in the sense that there's nothing linear about the Fibonacci numbers. Well, I guess in the sense that since Fn is a linear combination of Fn minus 1 and Fn minus 2, there's a bit of linearity, but when you look at these numbers, they definitely don't grow linearly, so it's perhaps not super natural to look at linear algebra, but in fact that turns out to be the best way of computing the Fibonacci numbers. So in order to talk about this, let me remind you that I had a bunch of various ways of computing the Fibonacci numbers, and then I fed it inputs that grew exponentially. So I asked Maple to compute the Fibonacci number at 2, 2 to the second, 2 to the third, 2 to the fourth, and so on. Of course, this will grow very fast in time because we are letting the input grow exponentially. So you see these very dramatic increases in time, and we cut it off at a certain level. We stop the first time we go above 10 seconds. And this actually this illustration comes from the book, so I think this is actually I went a little bit further, so I went to a minute there. So you see the first time is something less than a minute. That's the last one we kept. So I had various variations. Some of them didn't work. I haven't timed them. But you can see the very first one, which was the naive one, where I used no remember table, you see that this grows. It looks like it grows as bad as the other guys, but that's actually not true. It's much worse, and that's oops, wrong button. Well, you can see that if I just put out the if I just show you the observations, there's only one observation that comes up to the size, and then it just explodes. So I mean, the first way of doing this is clearly not good. But the other ones are sort of similar in time consumption. You can see this if I do a logarithmic plot. So this is a little bit confusing, right? Because I'm using a logarithmic scale on the y-axis, but in a sense I'm also using a logarithmic scale on the x-axis because I'm taking the n there and I'm applying 2 to the n. So there's sort of a hidden log setup here that is perhaps a little bit confusing, but you can see that actually if you sort of look what that means, it's you would expect that straight lines will somehow correspond to linear time, which is pretty good. But this one over here, the solid line, is the built-in method, which turns out to be a lot faster than all of the things that I tried to do in various ways of being clever about using the Binet formula and so on. So you can see I'm beat by the built-in way of making these computations. We can make this very clear if we run, I load the Fibonacci, the built-in one, and ask to use f timing on that, this time with 10 seconds. You can see that I can get much further than in my best attempt as far, which was to 2 to the 23. We'll have to wait a little bit. There it is. So you can see I go to 2 to the 29 without breaking the 10-second barrier. And that is a lot better than what I did, like 2 to the 23, I think was the best thing I could do in the other approach. So how is this possible? How can Maple be so much better than what I'm doing? Well, I'm sure it's because Maple is using linear algebra. And so the way that this works, and let me just sort of give you the idea, is that we look at this matrix here, 1, 1, 1, 0. And then we note that when we take powers of 1, 1, 1, 0, that will give us the Fibonacci numbers. So each matrix gives 3 Fibonacci numbers. So this one is Fibonacci number. I start with Fibonacci number 0 down here, then I have the first one here and the second one here. Now as I take powers, you'll see that the Fibonacci numbers come again this way. So I get 1, 2, 3, 5, 8, 13. But I also get 1, 2, 3, 5, 8, 13, and so on, like this. Right? So this looks like an inefficient way of computing. It's easy to see that you actually do get the Fibonacci numbers just by matrix multiplication. But how is this a good way of computing the Fibonacci numbers? Well, there is a trick we can do, right? So because what we can do is that, for instance, to get to the 8th power of A, we don't actually have to make 8 or 7 matrix multiplications, because we can be clever in the sense that we say, let's take the square of A. When I take the square of A, I get this matrix here, and then I take the square of that. I get this matrix here, and then I take the square of that, and I get this matrix here, right, which is 8 to the 8, right, because I've just written 8 as 2 times 2 times 2, and I've done this as squaring repeatedly. Right? But you see, this saves me computations, because to compute a square, I have to do one matrix multiplication of 2 by 2 matrices. Then to square again, I have to do another one, and to square again, I have to do another one. So I'm down to 3 rather than the 8 or 7 that I would need to get to 8 to the 8th. Right? 7, I guess, would be enough. And this, of course, I mean, for this small one, it doesn't really matter, but suppose that you were looking for a to the 256, well, then you're looking at 255 matrix multiplications as compared to 8. Right? So this is something that saves us a whole lot of time. And you can write a Fibonacci procedure this way, so it's based on the split command that we talked about earlier. So I'm taking a number like 100, and I'm asking Maple to write it out in binary form for me. This is like a bit string, so I have the digits of the binary number corresponding to the decimal number 100. So 100 is 64 plus 38 plus 32 plus 1, 2, 4. And so I'm just asking Maple to do this for me. Then what I can do in order to compute the 100th Fibonacci number, essentially I need to compute this matrix here, A, lifted to the 100th power. Right? So I multiply it by itself 100 times, but I can save time because I can compute A to the 64 by squaring A to the 32. And I can compute A to the 32 by squaring A to the 16, and so on. Now, to compute A to the 100, I can compute this as A to the 64 times A to the 32 times A to the 4. Right, so I'm not actually going to need A to the 16 or A to the 8 or A to the 2, but I need to compute them in order to get to A to the 64. Right, so my little program here works the way that it says, okay, how many digits does my binary number have? That's the number of powers that I need to compute, and then I just compute this. And then in order to get the Fibonacci number, I multiply the relevant choices of powers like this, right? So Maple unfortunately does this, that makes these things look a little bit very difficult to read. But what this means is that I'm just computing B is B times C. Right, so let me just quickly go through this program. I let M equals, first I take this, I split this out in the binary digits. I say how many digits are there, binary digits there are, call that M. I take A to be this matrix here, and I let B be the identity matrix 2 by 2. And then I'll go through from 1 to 1 less than the digits here, and I will say if the bit string is 1, then I will multiply on the matrix, the relevant power of A, and I will square. And then I keep doing this until the end. I know that the last digit has to be a 1, otherwise it wouldn't be the last digit. So I multiply on the final power, and that gives me that matrix that contains the number that I'm after, and I'm subtracting this. It happens to be at the 1, 2 coordinate. So you can see this. My program works exactly, it gives the right thing, and it works correctly in general, except that I'm not 100% sure that it will work on 0, right? So let's just do this, I hope. Yeah, so that's wrong. It should be 0. We could fix that, of course. But if I time my program here, you can see that that's actually faster than anything I've done this far. Oops. Just have to wait. It takes me to 2 to the 27, which is better than 2 to the 23, which was my record this far. It's not as good as the built-in one, and that's probably because I'm not using the most efficient way of doing my linear algebra, but you can see this is really very, very fast. And why is it so fast? Well, it's using, in a sense, if you think about what it is that I'm using to save time, I'm using some of the computational rules about matrices, right? So essentially it's the associative rule for matrix multiplication that tells me that in order to compute A to the 100, I can compute A to the 64 and multiply that by A to the 32 and A to the 4. And then I can use this successive squaring to save a lot of time. So this is a very simple-minded idea, but it's not really possible without linear algebra. And this is the point that I'm trying to make, that when you're trying to speed up things, look for linear algebra because it can very often take you places that you wouldn't be able to do without linear algebra.